The one where the motion looks really big.
Sit in the boat.
The one's laying differently on the bottom. See how they're facing a different direction? Grab one of those. Nope. Yep. All right, so we're going to define inertia. Inertia is a resistance of change. Is a resistance to change in motion. Okay, when I say change in motion, that includes speed, direction, or rest. Any questions so far? So inertia is basically known as Newton's first law. He has 3 laws of motion. You know it. You've been told it most of your life. An object in motion stays in motion. An object at rest stays at rest. No, I'm taking my notes.
Did you do the Pledge of Allegiance?
Huh?
I just not thought about that. We didn't do the Pledge
Not
of
yet,
Allegiance.
no.
Oh, crap.
So, an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. That is Newton's first law of motion. Any questions so far? All right, let's talk about this ball.
Oh, wait, can you do just for 5 seconds? Okay, I got it.
All right, let's talk about this ball on a ramp. What's going to happen if a force represented by this arrow is applied to that ball? It's going to go down that hill, that little ramp. There we go. Doop. Doop. Down the hill. Now, just as that force has allowed that ball to go down the ramp, and now it has gravity also helping, it's going to have a force acting against that motion. What do we call that force acting against the motion?
Gravity?
Not gravity.
Friction.
Friction.
Gravity drops, isn't it? Never mind. I'm just gonna do my math.
Friction acts against a motion. So now, if the same force is applied to the ball at the bottom of the ramp to go up it, is it going to just speed up at the same speed? No, it's not, right? Because now we're going to have a force that's causing it to go up the ramp, but friction and gravity act against that force. That ball's not going to go up at the same speed. It may not even reach the top of that ramp. However, if the ball was on a frictionless surface, and a force was applied to it, the ball would move forever on a frictionless surface, which would be like an air track is almost frictionless. We don't have a whole lot of readily available frictionless surfaces. Any questions so far? All right, let's look at this roller coaster ride. At W, the ball would move forever. At W, the cart is at rest. So if this was a roller coaster and you're in it, some force has to be applied to you to get you to move. This looks like a wooden roller coaster, so it's probably like a clanking sound as there's a machine running a belt or a chain to grab onto that coaster and pull it to the edge here. Once it gets the edge, that chain or belt or whatever is taken away. What helps that roller coaster go down the track? Gravity.
Wouldn't also be the weight of the object?
Yeah. The weight of something is due to the mass times the acceleration due to gravity. But what happens when our little cart here my people fell out, so yeah, sorry people. What happens to my cart right here? Does it just stop? No. So at this point, because you've had gravity and the force thereof, because of the mass times the acceleration, which we're going to talk about tomorrow, pushing this cart along, it gets to the bottom of this hill, it's going to go up the hill. Because of inertia. Inertia is going to keep that cart going. Now, is it going to be going as fast as it did down? Absolutely not, because now we've got friction, we've got air resistance, all that other things. But it's going to help it go up that hill. Now we have a little cart. Doo-doo-doo. At this point, what's going to help that cart go down now? Gravity again. Any questions about that? So that inertia is that resistance to the change in motion. If you've ever had to move something super heavy like a fridge, once you get it moving, you don't stop. That initial force needed to break that inertia is greater than the force you need to keep it moving. So the hardest part about pushing on something is getting it to start. Once you have it started, it's good to go. If you get, like, okay, listen. My love language, how I show I care for people, is active services, but like my ADD says no cleaning. I can garden, can't clean. So I cook, because fat people like to cook anyways. So it is very common for me to bring people chicken noodle soup, tamales, my broccoli cheddar soup better than Panera, I've been told. I don't know. I don't want to get crazy here. All this stuff. So it is very common for me to travel with food in my car. I have to belt it down, because if I'm not paying attention because my favorite song came on the radio, or a bird flew by, or there's a pretty colored car, whatever happens, and I don't see the car in front of me brake sharply, I'm going to have to slam on my brakes. If my broccoli cheese soup is not belted down in the car, what's going to happen to it?
It's gonna fly.
It's going to fly. Y'all have never cleaned melted cheddar out of a car's interior. It is not fun. Many a times. More times than what we probably need to discuss.
Do you drive a Jeep?
I do not drive a Jeep.
Okay. That was just a guess.
But that's because the soup is in motion and it doesn't get that memo to stop, so it continues in motion until it hits a force to stop. That force is usually the back of another seat or my dashboard, whatever it happens to be, and then of course it spills. Yes, it has a top on it, but I think you're being a little judgy on how I'm driving here. Regardless, the reason we wear seatbelts is that inertia. If you're going forward in a car, you have to slam on the brake. If that force of your seatbelt is not there to catch you and stop you, you will continue to move forward, minus the car. So that means you might move forward into the steering wheel. It might mean you move forward into the windshield. It might mean you move forward through the windshield. It kind of depends on how fast you're going. That is why we wear seatbelts, to help with that inertia, to keep us in the car. Any questions? Perfect. The last thing we need to cover here is this guy right here. This is a pendulum. Pendulum.
Got a D?
Yep. Pendulum. It's your spelling word of the week. We're going to test on Friday. I'm just joking. I will never test you on spelling. I will never, ever, 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 ever test you on spelling. Yeah, they did. It was a little funny.
I'm gonna make sure to spell it. Never mind.
I'm not going to catch it. If you can spell parallel, you're ahead of me. So, I mean, I have to really think about it. There's a lot of L's. It's a weird one. So, pendulum is a weight on a string. And it has some sort of axle at the top. And you apply a force to that, and it'll start to swing.
Oh, the thing's like two. hit each other?
That is Newton's cradle. That's different. This is one thing. This would be like if you put like a yo-yo, and you just went around. You're applying the force to the outside of that yo-yo to keep it going. If you can keep your axle really well lubricated, to reduce the coefficient of friction, it will go for quite a while. It swings due to an outside force acting on it. All right. Sorry. How's that? So then, what would happen to friction? What would happen to motion if friction didn't exist? I want you to answer that question right here. I'm not going to answer it. That's for you to answer. We will discuss it in a second. So write down something. I'm going to continue to color for about a minute and a half while you do that. All right. So what would happen to motion if friction didn't exist?
The speed would increase, or the motion would be faster, or the motion would be quicker.
Okay. So if you had an unbalanced force to push on it constantly, yes. If you had something like, I don't know, a ball in a frictionless environment, and it was going at 2 meters per second, it would go for 2 meters per second forever. And then when it hit something, it'd bounce off of that and continue to go 2 meters per second forever because of that lack of friction and those inelastic conditions. Y'all remember when you were in chemistry and you talked about that ideal Gauss law and the kinetic molecular theory? That's what this was talking about, where particles are all around us and they're constantly colliding and they're always having perfectly elastic conditions, so they're always moving. That's what would happen. It would be no bueno. We like friction.
So how would you answer this?
Can you put the motion would be faster and constant?
Well, it's only faster if there's an outside force acting on it.
Or that too? Well, so constant.
So I'd say if friction did not exist, then objects in motion would never stop moving.
Wait, just to make sure, whenever you were
Oh,
gone
mine.
that one day, you're not counting that, day 3? Hey, God, I mean day 40.
All
The one that,
right, so this is going to be due at the end of the period today. There was a miscommunication last period, so I want to make sure y'all look at the screen, please. This says inertia is when an object resists a change in motion. This resistance often occurs in the opposite direction of motion. Okay, this right here, you would say I agree or don't, and why. This, you would read and say true or false, and why. Here and why, here and why. They're not in columns. There's a dotted line here to separate them, but apparently that wasn't enough. Down here it says puzzled out. Connect the terms to the definitions. Watch out, one is missing. The one that's missing you would fill in. Are you all with me so far? It seems pretty simple, right? Okay, I want to actually do the know by sights. All right. We have a hamster wheel, person ice skating, person rubber building. All right, it says cross out the following non-examples or incorrect ideas. When a hamster runs in the wheel, does it have that type of motion?
Yes.
What happens if the hamster stops running? Like it gets up really, it's going super fast, and it stops running in the wheel. Yeah, that little baby goes, and he flies out. Does that happen? Yes, there's probably 200 TikTok videos I can pull up right now about it. Right? So, we're going to circle the check. So, this is inertia when the hamster stops running and the wheel spits him out. Okay, what about my ice skater? Does he use his back foot to push forward to have forward motion? Yes.
That's true.
Is that inertia?
He's using an outside force to change his state of motion, absolutely. That one can't happen. Why?
Because you fall back.
He does not have enough friction. Who can run up the side of a building? Spider-Man. Who else?
A lot of people.
The Fly, sticky people. Yeah.
There's some people who can actually.
He does it on the shield.
He does have a shield, but is it completely vertical? Not usually, right? It has a little bit of a.
It's like
The
All right.
Flash.
Oh, the
So,
Hulk.
The whole. The Flash does. He runs straight up.
it's just that fast. Though.
Yeah. Anything is
So how
possible.
does that work?
What's that?
that's a gecko foot. Geckos can run straight up a building.
Oh.
Why?
Because they're
They have
sticky.
like cups in their fingers.
They have like cups in their fingers that look like this. They're ridges. Those ridges increase the friction for that gecko. That's why they can hang upside down on a building. No big deal. We don't have that ability because we don't have those cups. We'd also have some abs, man, to keep us like straight while we ran up. Like you'd have to have some really core strength there. Core. We do not have the friction or the core strength to run up a building. So that's a no.